to the most preserved and places on Earth where we can study ancient history of our planet. For example, one has to visit South Africa, and you're all welcome to have a trip here, as in field trip, or visit South Africa to see the beautiful rocks. Next to it is a Zimbabwe craton, next to the Kapval craton, where we have green schist fascist rocks. So all these green boxes are representative of rocks which have undergone low-grade metamorphism, meaning that the rocks are well preserved, of low strain, and have potential to suggest or to at least provide evidence for primary signals of life or crustal evolution in a way. The other part we'll be discussing more is on the Indian Craton, mostly the Singham Craton, and we will be also traveling to Australia a bit to see the Pilbara Craton, to see some of this ancient history. Well, now that we would take a flight to all of these places and then to study them, but before that, we would want to also understand how the Hadean or the Eoarchean Earth was like. So this is actually an artist's impression, and imagine that we actually have to take the help of an artist, which is great, but at the same time, we do not have much in terms of Hadean Earth preserved. So most of the information is trapped in minerals. Sometimes we do have some Eoarchean crust in the form of TTGs or some gneisses here and there, but not much in terms of real rocks that we can study the Hadean or the Eoarchean times, right? So this is a time which is also getting more and more. I can use this term if I'm allowed to fancy, because the more we don't know anything, we get more and more curious and we want to study those, right? So basically, Hadean and Eoarchean are those time periods where we basically have not much of information, but we want to study that period of our Earth's history. Now, talking about Hadean Eoarchean time, India is a superb and a fantastic place. You can see all research over the years, over like a very short span of timeline, which has produced amazing results from the Singham Craton. And we can say Hadean to Eoarchean zircons are reigning in Singham. Otherwise, a recent research from the Kadapa detrital zircon record have also suggested that there are Hadean grains roughly around 4.1 billion years in age, which were also captured or found in the detrital zircon record of the quartzites from Kudappa, right? So India is a superb place to study Archean or early Earth, and with that comes the fact that I should be allowed to say this. Actually, this is one of my slides which I really love, and I would like to say that this is a copyright slide for me. So I also teach, and while teaching, I actually familiarize the students like how we should visualize ourselves at looking at something which we have no information. And we all love Mona Lisa for the beauty and the portrait of that. But let's say, imagine we have to find similarity in rocks, and we want to understand how rocks of old age can be turned down into Mona Lisa's portrait. So let's say if old rocks, meaning elderly Mona Lisa's portrait, and this portrait was thrown away in a garbage or put aside somewhere, and after several hundreds of years, someone comes up and picks up that photo of that same portrait and tries to unravel the eyes or the nose of the actual Mona Lisa, how it looked like. It's a very daunting task, right? So actually, the reconstruction of the Archean history is super complicated, and it's very difficult. So the process of going back and forth and trying to unravel the processes is complicated, intricate, and many other vocabs that you can find, but it's always a task which everybody has to do very carefully. If not done well, then you can be under a lot of strain. So, how is the Archean Earth, and what do we know about the Archean Earth? So, basically, this is again an artist's impression, and I really like this imagination how we look at the Archean Earth. So, this photo actually captures some of the salient features what we might not have on our modern planet, right? So, what we have here is that the Earth was covered by volcanic eruptions, right? Those volcanic eruptions resulted in gases, toxic gases, which were such as like carbon monoxide, sulfur dioxide, hydrogen sulfide, you name them, you have them. The moon was much closer back then, right? And there was a thick absence or or rather an absence of ozone. There were other events such as bolide impacts were very frequent. Oceans were primitive and they were still there. And probably under such conditions, when the moon was much closer to us as of now today, uh, life did exist. And we will touch upon those facts a bit later in this talk. So now, as I've already introduced, probably life started off during this rocky patches of our Earth's history. How and where and under what conditions? So it's a very difficult task. Again, it's like looking for a needle in a haystack, right? I mean, there's always an attempt to look for the oldest traces of life and how we can determine that this is life exactly. And I can go on and have a different talk on that. But today we rather focus on something where we would see exactly how life is preserved in the ancient rock record. So the first place, which exactly is one of the most detailed, um, in a way, studied area locality you can call, where earlier it has been investigated in a lot of detail, is actually Greenland. And I was very fortunate to visit Greenland last year. It was a trip to remember, and I hope that I will go there again because of my collaborations, and I'm working also actively on the ISWA supracrustals. So it allowed me to see rocks which are as old as 3.9 billion years. And the context about Greenland is very different to what we have in other places to study ancient Earth. So that field trips here in Greenland are not a matter of joke. You actually are under harsh conditions. You usually are subjected to boat trips or rides in helicopters, and you don't have any. Okay, if you're not in this, if you're in the city, then you can do a bit of geology here and there. But if you are willing to see or investigate geology in the far remote places and you don't have the luxury to take your car, rather you have to be dependent on the boats or the helicopters. So this is a kind of a very difficult and a process which everybody has to deal with when they go to Greenland. So we were having field trips which were organized with boats and helicopters. Now, as I've already mentioned, that Greenland is such a beautiful place to study ancient geology, and the geology starts roughly around the time period of 3.9. We have gneisses, from there the gneisses, and then we have the age of that close to about 3.9 billion years. And in the year 1996, if I'm not wrong, scientist named Stephen Moitzes, he studied some of these banded rocks, which are shown here to the right. And to the left is a photo of the Aquileia Island, one of the probably the most famous islands in Greenland and probably in the world. It's actually a UNESCO heritage site also. And why it's a heritage site? Because in this year, 1996, there was a discovery that they have found certain traces of organics within apatites. And the argument was presented that these apatites have organic material. And if this rock is of 3.9 billion years, then this apatite should be 3.9 billion years, meaning that the organics are also 3.9 billion years, which unfortunately was not the case. Later on, few researchers studied this whole context and they found that the apatites were actually much younger than the rock. So may have been that the apatite re-equilibrated at a much later stage, and the age of this apatite was around 1.6 billion years or so, so much younger. So the organic material was of not 3.9 billion years, but much younger. Now, um, other than that, there's also fantastic research which have been conducted from the Nook area. So to the left is a geological map, if you can see. To the western part, we have Nook, and where actually is the airport if you were to go and study the Greenlandic rocks. Here to the east is the Iswa supracrustal belt. Here's a geologic map to show you some of the lithostratigraphic units. Mostly they are made up of TTG gneisses, amphibolites, and some meta sediments. And the wonderful part about this Iswa greenstone or supracrustal belt is that there were some turbidites which were studied by Minik Rosing in 1999. And this was a major milestone in terms of early Earth research, early life research, whatever you may call. This turbidite did host carbon, and the actual date of these turbidites were dated around 3.7 billion years. And they actually, Minik himself studied this rock. He found this carbon to be highly depleted, meaning that isotopically lighter carbon, close to about minus 28, if I remember the numbers correctly. And he suggested that this is definitively a chemical signature of life preserved in these turbidites. Apart from that, many other research has been conducted on the Greenlandic rocks. One such kind was presented in 2016 when I started my PhD in South Africa during the IGC. I remember coming this across this paper, and this was a very paper which was always in the news, that emergence of life, stromatolites at around 3.7. So life may have been the beginning of life may have been even older. However, to all the surprise and to the amusement, this talk of this stromatolite having at 3.7 was discarded or rather refuted by other scientists such as Abigail Elwood and co-authors who went to Greenland and studied these rocks, and then they argued that these stromatolitic structures are rather made up of some strain and deformation due to structural imprints and not biological factors playing into the formation of these rocks. So there have been numerous papers and articles on this kind of research, but so far that I can say that the chemical science of life did exist and do exist at 3.7 billion years. Now, moving from the Eoarchean to the Paleoarchean time, when we do have preserved rocks and better preserved areas, as I've already mentioned, South Africa, India, and Australia, what we see in common to all these places are pillow-basalts. And this pillow-basalts, which is shown here to the right, is really a representation of a major variety of rocks. So Paleoarchean greenstones are mostly made up of submarine mafic volcanic eruptions. Now, what does it mean? It means that volcanic eruptions were mostly submarine in condition. Whatever eruptions happen, most of it happened submarine, and with that you have formation of or rather now preserved pillow-basaltic sequence in all these greenstone sequences. Apart from pillow-basalts, you have some kumatiites and other ultramafic rocks which make up 70% of this greenstone successions, right? And these greenstones are also unique. Why? Because they are of low strain, they have bridges facies metamorphic mineral assemblages, and the metamorphism is close to about 350 to roughly around 400 degrees or something. So this is something quite unique. And apart from volcanic rocks, there are also association of carbonaceous dirt brine, very important, and will be discussed in detail. Now, today's talk, we will not have enough time to go through all the aspects of Paleoarchean Earth, but there are certain features which are also very unique, which were only caught from the ancient history of our Earth during the Paleoarchean times. For example, the processes such as our understanding on the magnetic field of our ancient Earth. How was the magnetic field? Was it stronger or was it weaker than our modern day magnetic field? So I'm collaborating with researchers who have a strong research um, um, kind of an agenda on the Earth's magnetic field during the Archean time, and they have done phenomenal research with that. There are also aspects like impact layers, which means that there were bombardments from extraterrestrial sources, and with that you have preservation of some of these events in terms of some event beds, right? So these are impact spiral layers, which are shown here to the right. Now, then there are also tsunamites or tsunami deposits, which are also preserved from the Paleoarchean rock record. So these are very pristine signals, not in terms of life itself, but in terms of our own Earth, what we know of our young Earth. And it comes largely from the Paleoarchean times. Now, if we move to Meso or Neo-Archean, there's a slight shift or transition. It's with like the time that we have from winter to summer, and here also with time the earth changed, and here there were more evolved continents. And what does it mean for the fate of our earth's history? It means that there were volcanic eruption which were capable of having lava plains, such as if you would visit Hawaii or any other place where modern day eruptions are taking place in the continents. Of course, there's also submarine eruptions, but then you have continents where these lavas are probably progressing. This to the right is a photo of one such lava, which actually preserves Pahoy Hoi texture. It's a fossilized lava texture, which is probably 3 billion years in age. To the bottom is an example from India from the Singhbum Craton, where this shows cross-bedded sandstones, which are actually remnants of some cratonic cover sequence. So now there's this distinct difference between Paleoarchean to Neoarchean or Mesoarchean, roughly, where you have sandstones coming into action, carbonate platforms, iron formations, and then basaltic eruptions or more volcanic eruptions, where on the land, meaning subaerial volcanism was predominant. So now what we have is a bit of an idea and a knowledge on the time frames. But now, if we were to study the Archean times, we will have to go to South Africa. Everyone who has done Archean geology has been in this continent and especially South Africa to see the amazing geology that they preserve. So this is a map of the simple map of the geology of the Barberton Greenstone Belt. From the lowest to the uppermost unit, we have a stratigraphic slice of like a cake. You know, if you want to cut a cake and then see the lowermost part, which is the oldest, then you have something in between, then the youngest. So the lowermost ones belongs to the Onverberg group, mostly made up of submarine mafic ultramafic volcanic sequence. Followed by that we have Victory group, which are also volcano-sedimentary succession, slightly younger in age, 3.25 billion years to 3.23 billion years. And the yellow colored portions are mostly the Moody's group sandstones. And recently there was a huge drilling project conducted on the Moody's sandstone to understand the earliest habitats of life from the Moody's group, right? So the greenstones here are intruded by numerous granitoids and TTGs, which are shown here in the background in pink. And these are typical association of granite greenstone terrains, where you have associations of greenstones with granites, TTGs of different kinds and different ages. Now, this being said, Barberton Makanswa Mountains, my geological crush, was declared as the World Heritage Site in the year 2018 because of this fantastic geology and the amazing landscape, which hosts probably some of the oldest rocks on this planet, right? So, this is an amazing place to visit and study geology, mostly our young Earth in its own form. Now, what do we see in terms of Archean early life from Barberton? So this to the left is a photo of the Barberton greenstone sequence, and here we have TTGs of different ages ranging from 3.5 to 3 billion years and even much younger. Now here what we had, and I was very fortunate to also see these fossils for the first time from Axel, who showed me this in 2011 when I visited South Africa. This might look like a random bunch of needles in a siliceous matrix, but to all those microbial enthusiasts, these are nothing else but microbes, which are close to about a micrometer in diameter sometimes. And the length can be a bit larger. It could be like 100 micrometers or maybe even 80 to 200 sometimes. So they are all distributed in this siliceous matrix. So they are remnants of life close to about 3.4 billion years. And these are bona fide evidence of life. Now, apart from the Barberton Greenstone Belt, some form of research also did take place in the non-Winnie Greenstone Belt, where my current research is based. I'm working actively on the non-Winnie Greenstone Belt with Alan Wilson, who has been working in non-Winnie for a long time. And now here we have the oldest stromatolites of the African continent. They are 3.4 billion years in age. You can see the domal stromatolitic structure, which comes from this non-Winnie area. Now, apart from that, what we have is that we have Pongola supergroup, which also hosts stromatolites. They are roughly dated at around 3 billion years or so. So then these are widespread evidence of life from South Africa. Now, talking about the Archean record of Australia, you have greenstones and granites, and you have also similar association of rocks, but there you have also different microfossils, which have been discussed in detail by Kenichiro Sugitani. And these are colonies of microbes, lenticular, lensoidal shape. They are forming some assemblages, which will be also introduced later in the talk. So apart from that, what we have is that we have microfossils, and then we have the world's oldest undisputed evidence of macroscopic fossilized evidence of stromatolite from the Dresser Formation. So these are all examples of Archean life. Now moving to the Singmum Craton, and where we have the Dietary Greenstone Belt, where I did my research and I mapped the central portion of the greenstone. From the base to the top, we have volcano-sedimentary successions. At the base, we have mafic, ultramafic volcanic rocks. Thereafter, we have felsic volcanic rock sediments. Followed by that, we have more sediments with clastic and orthochemical sediments at the top, and we have mafic volcanic rocks at the upper part of the greenstone sequence. So these are shown here in different colors. And this greenstone is intruded by numerous granitoids and TTGs. And the yellow colored portion is largely of the Mahagiri quartzites, which are sitting unconformably on top of this greenstone. And here also, in our recent study, we have found some similar microbial structures. Apart from that, the Mesoarchean to Neo-Archean record of the Singmum Craton is a place which deserves standing, and it has so much wealth in terms of economic resources, but also in terms of life. There's stromatolites, and these are some of the photos which were recently in our one of our publication or contribution, which we studied from this area in the Koira group of rocks. In our recent contribution, we also have highlighted some of the organic material which is preserved in the stromatolites of the Zimbabwe craton, and this to the left is a photo of the Zimbabwe greenstone succession. So everything in green are greenstones, much younger, close to Neo-Archean in time. However, the pink colored portions are granitoids and TTGs. And in the center of the map, you have the Great Dyke, the famous Great Dyke. And here, to our great surprise, some of the stromatolites were studied to understand the grade of metamorphism based on the preservation of carbonaceous material. And we found that some stromatolites were rather well preserved at lower Grinch's or rather Grinch's grade of metamorphism, and some even have suffered amphibolite fascist metamorphism. Now that you have seen some form of life, and if you were to travel these places, you would come across all these stromatolites, visit Australia, India, South Africa. But more importantly, if you go to Australia, if you travel further up from Perth, you would visit this place called Shark Bay, which is a coastal plain. And then if you go there, you will see these features, which are nothing but modern day stromatolites. And the funny story is that if you move further, few hundred kilometers away from Shark Bay, you will have fossilized stromatolites, their fossilized equivalents. So this is very amazing, the geology and the type of rocks that we host in the Archean. And the other fact that we are also very interested, and a large part of research of the Archean history is also focused on the hydrothermal processes. This has remained an core and an integral part of the Archean times. So to the left is a photo which shows some bedded cherts shown here in stipple colored, and the arrows are mostly represented by some hydrothermal cherts. This is a photo of one such formation of such rock assemblage, rather we can say. And so the pillow basalts are cross-cut by some younger chert veins or chert dikes, and above that we have silicified cap units. So these are quite diagnostic, and you come across them also in South Africa, India, and to our surprise, we do have them in our modern Earth. Hydrothermal processes are very prominent, and deep sea vents, deep sea chimneys are also quite actively operating in the modern deep sea environment. So these processes were kind of similar, but slightly operating in a different way. So there's a bit of similarity and some dissimilarities, which we will discuss in a different talk some other day. Apart from that, deep sea vents, we have also microorganisms which are prokaryotes, and they do harbor these deep sea vent settings, and some of them are in the form of chemotropes or chemoheterotrophs. And remarkable research was conducted by Schoff or Walsh from Australia and South Africa. So these are very unique features and unique microfossils preserved in these low-grade rocks. Such a kind of study which I've already highlighted is these threads or bundles of needles, which comes from the South African Archean record. This is a representation of one such kind of kerogenous component which is distributed in this siliceous matrix and now seen in this three-dimensional orientation. The emerald green to bluish color are representative of the structure of microfossils. So these are very detailed and careful work conducted on the 3.4 billion year rock record of South Africa. Apart from that, what we have are planktonic microorganisms from the Archean. They are mostly represented by spheroids or lensoids, which have a diameter close to about 30 micrometers to probably 150. Sometimes they can be even larger. And they sometimes have smooth walls or sometimes can be corrugated or discontinuous, potentially some preservational biasness, or maybe it's supposed to be like that. Otherwise, they also have some association, as I've already mentioned, that they can be in colonies and found in Australia, India, and now in South Africa. This is one such example. If you study the rocks of the Onwawa group, so the lowermost pile is volcanic rocks. However, we have sediments, and the sediments of the Buck Reef Chert dating back to 3.4 billion years that host banded cherts with some carbonaceous remains do host these traces of solitary spheroids. Now, if you move to the Paleoarchean record of the Strelepool Formation, roughly around the same time, you have these microfossils which are also solitary to some colonial assemblages. And this were extensively studied by Kenichiro Sugitani. And to us, for the Indian community, during my study in the Daitari Greenstone Belt, I came across similar rocks, and I also studied several numerous thin sections, probably 200, 300. I don't even know how many thin sections I have in my drawers now, but then I did come across some similar looking microbial structures. So they do occur, but not uh, in a in abundance. They are very rare. So now, if we move from the Paleoarchean planktonic microbiota to the more younger times, such as the Mesoarchean or the Neoarchean times, you see that there are association of solitary spheroids, but then there are also spheroids which are actually in colonies. And these colonies are now here to the right portion at the bottom part of the slide is shown here in golden yellow fringes. These golden yellow fringes are nothing but representative of the carbonaceous component, and they are always studied under the Raman spectroscopic microscope. Now, this quartzite or chert unit is quite unique from the Farrell quartzite section in Australia, where they host a variety of these fossils, and this has been studied by many authors, including myself. And we are having a new every day. There's a new context and a new idea about this kind of planktonic life during the Archean. So now moving to the final part of today's talk, and what we have is very interesting. Now, what I've highlighted since the first time is that our young Earth, or as we know of the time periods such as the Hadean or the Eoarchean, hardly preserves any primary signals in terms of metabolic pathways or life. But coming from the Paleoarchean time, we have enough information, enough of knowledge on what kind of metabolic pathways, what kind of microbes, how they did harbor the ancient environment. So, to the fact that we know and we have seen that since 3.5 to 3 billion years or even younger times, we have bona fide evidence of macroscopic life in all these places where rocks are well preserved, such as Australia, India, and South Africa. You see stromatolites, which are probably remnant of some phototrophic microorganisms. Then you have organisms which are planktonic, meaning that they could swim and harbor any form of environment during the ancient times. And there were also organisms which I've shown which were thread-like bundles or needles, which actually harbor the deep sea environments, right? So this, to me, looks like from 3.5 to 2.5 billion years, there was actually a biological insurgence, an insurgence which was probably 1,000 million years. And this actually suggests that life was not only there, but in abundance. And there was prolific life actually in all different corners of environment. So basically, Archean is the time to be in, to study the curious earth and to understand more and more on the dynamics of the different microorganisms. And what we have at the bottom part is a very famous compilation by Tim Lyons in 2014 in Nature, where they argued that there was a step or rise in oxygen at around 2.5 billion years. And this was marked by the global great oxidation event. What we see, or what we have seen now, is that since 3.5 billion years, it took time for us to accumulate all these organisms to have survived and thrived and flourished and have enormously contributed in shaping this planet. Probably that was maybe one of those reasons why we had elevated levels of oxygen in the atmosphere by 2.5 billion years or so. And to the conclusion part, what kind of a take home message that we can get? And this is actually a compilation from my PhD. What I like here is that it's actually a representation of our dynamic Earth, and it's unique because we have these conditions on Earth which were so different than our modern Earth. There were meteorite bombardments, no ozone, immense volcanic eruptions. The sun's luminosity may have been weak or something, and even despite these conditions, life evolved and flourished, right? So this brings us to the part that we have benthic microorganisms which harness the energy of sun, as in phototrophic microbes. There were also planktonic microbes which we have seen with tails and appendages linked to one another, may have been solitary sometimes or may have been in groups sometimes. Maybe they were in friends or enjoying their companies. And there were also deep sea environments which did harbor filamentous microbes. So life was abundant and prolific in those oceans. And some have also argued that life did exist in some kind of land, if there was a land during the Paleoarctic times. So coming to the final part of our discussion, and if some of you are looking for any form of extraterrestrial intelligence, I would want to say that we have a wealth of information what we can achieve from our modern Earth in terms of understanding the curious young Earth and go back in time to study the Earth and how conditions were. Actually, we know something, but we would know many things if many of us can contribute to this early Earth research, right? And so the conditions were so unique. They were these conditions which we have been discussing so far, but probably conditions like this do exist in different planets or moons, such as Europa and Enceladus or many other rocky bodies elsewhere. But for that, we would need to understand our own Earth, try to study it more in more detail, and then bring an analogy, and then have more and more insights and gain better insights to go and look for life or extraterrestrial intelligence, if any, elsewhere. With that, I would like to thank the different collaborators, institutes, and people who have come and contributed to this research, have really helped me understanding early Earth. First and foremost, my PhD supervisor Axel and many other collaborators, which you see in this slide, have really contributed of like understanding the early Earth conditions. And this is a photo which I also like. Probably we will have many other visitors, or maybe one day we will visit any other system or space in this cosmos. But what remains integral to us and to me actually is that our own planet and what we have is very special. So we should conserve and reserve this for the future us to have an exploration elsewhere if required, right? And with that, I would like to thank my sponsors and committee and people who have really helped me and sponsored my research, helped me through fundings and discussions and stays and accommodation and all sorts of kind of things that you need for research. So I really thank all of them, and I thank you for being a lovely audience. Thank you so much.
Thank you, Jaganmoy, for a wonderful talk. So it is really very the curious case is really very nice, and it's and your talk is very interesting, enlightening. So I would ask the the audience to ask for any question if you have to Jaganmoy.
Did you? I just have one question. Were you able to hear everything and see all the
Yeah,
slides?
yeah,
Okay, great.
I did.
Thank you so much.
I did. And I have a question.
Great.
Like by the time,
Sure.
so that is that from 3.5 to 2.5 billionaire, we have very yeah 1 billionaire, and we have very small amount of preserved evidence of life. Okay, and there are planktons, microorganisms basically. But
Yeah.
now we see that in say last 65 million years, there's thrive of life. So,
Mhm.
do you think that this this small amount of life in 1 billion year, what we are getting is due to the lack of preservation or the higher temperature, I mean higher heat, or the limitation of oxygen supply? What could be the major reason of having only this uh, microorganisms level of life?
When during the Archean, you mean?
Yeah, yeah. I mean,
Oh, yeah, yeah, yeah.
whether we
Well,
are we are not getting the actual result, or there is actually this kind of chemical, uh, I mean the atmospheric, or I mean the situation is not good for thriving more organisms.
well, it's can you hear me?
Yeah.
Okay. So basically, if I were to answer this, I were to answer this in a very um, a clean way that I understand these processes. The processes during the Archean was very different to. I mean, you have seen that there was no oxygen to produce enough ozone, and with there's a lot with aerobic respiration, right? So at the time when the eukaryotes rose at like 1.7 billion years or so, but with aerobic respiration there could be a process where the body shape or the size could be bigger, right?
Mhm.
And the processes of metabolism and nutrient supplies may have also evolved with that time. Like in a way, what I understand is that more and more the Archean crust was more mafic in nature, and then the nutrients or metabolic ingredients, let's say nickel was abundant, magnesium was abundant, but certain other, like let's say vanadium, probably was there. I mean, there was enough vanadium, but phosphorus was scanty, right? So then
Mhm.
you have scanty. I mean, it was there, but not that too much to the extent that it is now on our modern day. So, I mean, there are many factors, biologically driven, that can um, actually result in like a smaller shape. And I think that if you see, if how to say it, like there is more and more of that discussion, like how do we have that? So basically, if you see those microfossils which are of like a size of like 30 to 150 microns, which I've shown, it's actually not really prokaryote. So we even don't know what they are, and it's
Mhm.
surprising that are they really prokaryotes, or what is going on there, because they should not be there in the Archean times, or we don't actually know if they have any modern counterparts. So the size
Yeah, and the
remains a big.
actual cell cannot be preserved due to the temperature and.
Yeah, if you cook if you cook the sediments, then you probably would cook or not cook, but then you would not preserve the entire
Mhm.
structure. But then in some very well preserved rocks, like let's say the Rhine chert, or if you look from the, which one is the other chert? There's a chert from, there's a famous chert. I'm now getting it here, but not in my. It's in Canada. I forgot the name of the chert. It's not Rhine, but there is this chert which has these microfossils, and then they are very well preserved. So it's also about the preservation, but some of these fossils are very well preserved, coming to the point that if they have small or large size, I think it's a lot more to do with the respiration, and then to do with their requirement at that time, how they required, what they required, and the energy and the resources. A lot of my research now is also emphasizing on the stress response behavior of how these early microbes actually did respond to those kind of environments, and probably we think that those environments are harsh for them or for us actually, like with no ozone, no atmosphere and things like that, but maybe they were enjoying those environments. So there are this kind of a thing. But with the onset of oxygen, I think many things changed, and then we could
Exactly.
we could
Exactly.
we could do many things, we could grow big, I think.
Okay, we have a
So,
question from Anushka. Apart from microfossils and zircon dating, is there any other method to date Archean rocks?
well, first of all, there's a catch here. We don't get to date Archean rocks based on the fossils. There's nothing like an approach where we apply, like in foraminiferal research, or like, let's say, modern day fossil research, where we have an ammonite and then we give an age. We have not gone to that far where we find an index fossil for that. So first of all, I would like to clarify, we don't give an age of a lithology based on a microfossil, let's say, for example. So we are not yet at that stage to do that. Apart from that, dating, zircon is one. We can date metamorphic events with monazite, rutile. We can date apatites, but then they have like certain, benefits, and also things like they don't give the closure temperature as zircon gives. So zircon gives you exactly the temperature of the magmatic event. So there are things like that. But yeah, we usually use zircon, rutile, monazite, apatite, and yeah, these are the minerals which we usually look for dating rocks.
Okay.
Hello, I have a question.
Mm-hmm. Go
Please.
Hello,
ahead. Yes, I can listen.
can you hear me? So, so thank
Yes,
you for the wonderful presentation.
it's my
So,
pleasure.
so actually, my own is just observation.
Yep.
Since you are not dating the major rocks types in your work based on the fossils, it's only based on the metamorphic rocks with the zircon and what have you preserved in them. So, how can you see to incorporate the idea of the plate tectonics into this your research? Because most of the marine organisms that you are getting from the Australia, South Africa, and India, you even mentioned that mostly come from the submarine and deep marine environment. So how can you see the relationship of your research with the kind of plate activities, the kind of subduction between the continental and the oceanic crust, which maybe is responsible in bringing out this microorganism or marine organism onto these rocks during the subduction metamorphose most of these rocks at the crustal level. So that's my observation.
Okay, so firstly, we do not know exactly on this time frame that plate tectonics did exist in the Archean or the Hadean, right? There's no evidence that we can, apart from the research which are controversial, we have no clue whatsoever suggesting plate tectonics on ancient Earth, right? That being said, what we know is that these ancient greenstones are with TTGs, and there's no subduction signals that we can easily pick up from these TTGs or the volcanic rocks. So what we have are these preserved slivers of well documented rocks in terms of volcanic or sedimentary rocks. So they are preserved, nothing happened to them because they were mostly ancient cratons and they didn't do a lot. There was not much of tectonic activity in terms of destruction. They did destroy some form of the upper crustal levels, but then sometimes you have mid crustal levels or even lower crustal levels which are well preserved, and sometimes you have the slivers which are also high grade gneisses and TTGs and amphibolites which are representation of that. But anyway, some form of it may have been already eroded away because of the erosion. I don't think there was any plate tectonics to bring up these oceanic sediments. They were just, oceanic plateaus, oceanic environments where this volcanic eruption did take place, and then there were also younger crustal blocks which were added, like the TTGs and the granites. So plate tectonics had no role in kind of bringing or preserving these rocks, and no role in actually microfossil or microorganisms in this kind of rock assemblages. So plate tectonics has no link in this. And basically we also, so the last part which I want to add is that we actually have no information on the paleogeographic reconstruction of where Australia was at that time, where India was, where South Africa was, and what were they together? Were they together? They were not together. Probably Earth was operating at the same kind of a geologic process at the same in the same time frame. Like let's say what is happening on modern Earth, let's say in the Himalayas, is not happening in Czech Republic, for example, or maybe in Australia. But mountain building processes are very different to, let's say, subduction zones. So processes on Earth are very unique, and maybe similar processes happened during the Archean times, which were captured in these localities of Australia, India, South Africa, or some in Greenland. That's
Thank
it.
you
But
very much for this clarification and about this plate tectonics and all.
no, yeah. So plate tectonics was not. There are no evidence
Yeah,
of
it's
plate
not.
tectonics.
So, what region? Another question from Onindo. What region of the Singboom crater are the microfossils found?
So basically, it's from the southern part, and I where I did my PhD, I highlighted the area Daitari. It
Mm-hmm.
was actually where we found these greenstones with volcanic rocks and some sediments, and these sediments did host carbonaceous material. And in some of these thin sections, you do come across these microbial structures, which looks very similar to the ones which have been described from Australia and South Africa. But till date, we are not sure, certainly sure, like what is their affinity. But yes, to answer your question, roughly it comes from the southern part of Singhbum, from the Itari Greenstone Belt.
Thank you. Is there any other question? So, thank you, Jaganmoy, for your wonderful talk and all the question and answers. And it's really, really uh, yeah, encouraging and enriching talk. Uh, okay, so yeah,
Thank you so much.
Hi, Jaganmoy, am I audible?
yeah.
Yes,
Can you put some light on the future prospect of those who want to do research on this field? What could the opportunity for them? Means if
yeah.
anyone interested to do some research.
Yeah. So actually, basically, like I've said, that Archean Earth is very. It has been, and it will always probably be a place where most geochemists, geobiologists, and geologists are interested to study in terms of structure deformations, isotope geology, microfossil research. So what one can do is actually have an idea, like, okay, what do I want to achieve in the next 5 years or 10 years of my research. Like let's say if I want to do research on microfossil, then I would rather emphasize on the aspect of contacting people, or rather communicating with people in the community who are more specialized of that topic. Okay, now if you are a student who is interested in crustal evolution or processes of like crust formation during the Archean, right? So then you would want to see yourself getting to that point where you'd want to actually communicate and discuss or talk with people who are actually conducting research on crustal evolution, for example. So there's all of that. But firstly, I would be very happy if you want to discuss, or let's say talk and share your ideas, and if you have anything that I can help with. I've been working, and lately we have a very strong community, or like a group of earlier geochemists and geobiologists who are working in close connection. And possibly if there is anyone who is interested to work on early Earth, I can get in contact with people who are actively conducting this kind of research. So there's enough opportunity, there's enough resources, there's a lot of funding, because people are really curious to know a lot, and there's more and more non-traditional isotopes. And despite the fact that traditional isotopes have been in the market for a long time, but then there's also more and more ideas about early Earth, how it can be done. So there's more and more geochemistry to be done. There's more and more microfossil research to be done. So yeah, if you are up for one or several factors that you want to add in your research profile or career, then you choose that, you contact that group, or then you contact the community, and then you can really get to the point in a few, in just some few emails. Or if you are interested, I can also, if I can do something, I'll be very happy to help you. So yeah, feel free to contact. We have a good community here in South Africa which can fund for early earth research and early life research. So it's all good because we have a lot of early earth preserved in the South African continent. So there's still more to do, and yeah, if you are interested, then you can surely contact.
Thank you, Jaganmoy. Thank you. Thanks.
Thank you so much.
Okay, so again, I think now we should thanking everyone, IIRES, and others who have helped us of um, doing this session. Everyone who is operating this YouTube live, thank you very much for having such a wonderful lecture. And we are looking forward for the next lecture, and these are really helping the students as well as the researchers in communicating. And thanks again, Jaganmoy,
Oh,
for
thank you so much. It was a pleasure, and it was a pleasure to be with you all and to share whatever little that I know of the curious young earth.
yes, definitely, definitely.
So
Okay,
okay, thank you so much.
thank you.
Thank you,
You're welcome.
Keep,
Jaganmoy. And we expect your in future also you will have to contribute, and we expect some a great some more contribution from your side. Actually,
okay.
in India there are a lot of students, there are a lot of people. They are actually interested to do this kind of research, and if we get you, if you are interested, then definitely we'll try to get develop something for Brigham research actually. Okay.
Yeah.
Thank you so much. You accept our invitation, and it's a fantastic talk. Actually, I really enjoyed it.
Thank you so much
Definitely,
for this opportunity. It
definitely.
was lovely. Thank you.
Thank
I
you.
also really enjoyed it. It's,
Thank you, Chandra. Thank you so much. Keep well then.
yeah.
Bye.
Bye.
Bye.